Good evening, students. So today, day 30. In fact, we have done a lot more. Not day 30 today for our course actually. Okay, because we started on 20th of March, and today is 27th of April. So it is almost like how many days? Around 37 days are over. Okay. All right. So then, what we had, we yesterday we discussed about wave optics. In wave optics, we finished interference, Young's double slit experiment. So remaining was diffraction. So diffraction basically is what? Bending of light. Okay. Bending of light from what? Bending of light through sharp edges. Through sharp edges and small openings. And small openings. Okay. Whenever there is a sharp edge whose we can compare it with wavelength of the light, then bending will happen. Whenever very small opening is there, which again we can compare with the wavelength of light, there will be bending. Right? Two types of diffraction patterns we have. One is given by Fresnel and one is given by Fraunhofer. Okay, we study Fraunhofer diffraction pattern. Okay, we study Fraunhofer. Fraunhofer diffraction pattern. What he says? He says that we are going to consider plane wave front. That means the source is at infinite distance. Source is at infinity. Okay, which wave front? Plane wave front. Fresnel says when the source is placed at a finite distance. That we are not studying. Okay. Fresnel diffraction. Diffraction. Okay, what is that? When source is placed at finite distance. When source is at finite distance. Okay, this we are studying. But for this also, as I told you that distance or the opening between two sources or small opening that we have should be of the size of wavelength or comparable to the size of wavelength of light. And one more thing is there. Now, when we say diffraction, in diffraction also what is happening? In diffraction also interference happens. Okay. So, if suppose we say, okay, here we take openings. So, this is the opening. Okay. From this side what is coming? Plane wave fronts are coming. Plane wave front, we know that in that one what we can show? We can show this is how the light is coming. Okay. This is how the light is coming. In this way. And wavefront will be what? Wavefronts are always perpendicular to the rays of light. We know that, okay. So plane wavefront it will be like this. Now this is the opening. Now in this opening you can see that this is one edge over here, this is one edge. So if we are going to talk about this alone and we are going to have a screen here. Here is a screen. Okay. So bending is happening, bending of light is happening from here also, it's happening from here also. So the rays are going to interfere. Maybe suppose this is the point. Like this is the bending and here also the bending is like this. Okay. You can see that there is certain path difference for interference. Okay. So what will happen? There will be certain intensity developed because interference is happening. Right. So this is bending. Bending of light. Now, there is one criteria in which it says that what should be the minimum distance between sources and source and the slit. Now sources. Here there is one opening only. One slit. Young's double slit experiment means there we had two slits. Here we have one slit alone. Okay. So this is one source only. Okay. So what is the separation between this source and the screen so that we can observe this diffraction? That is called Fresnel distance. That is given by Fresnel. Normally we represent it with what? D. And this separation between two edges of this slit is D. Then D equal to D square by 4 lambda. Okay, D equal to D square by 4 lambda is the distance between your source and the screen. Then only we are going to observe this pattern which is called diffraction. Okay, so this is which distance? This is Fresnel's distance. So even when we are studying Fraunhofer diffraction, we are considering this should be the minimum distance between source and the screen. Then only we can see the bending. If this distance is less than this, then bending we will not see. We will see that light is traveling in straight line only. That means when the screen will go very close to each other. Okay, screen will be very close to this opening. Right. So this is what Fresnel's distance is. Alright. Now let's come back to this point where this interference is happening. Okay, let's say this point is P. So here again we are going to talk about path difference, we are again going to talk about phase difference, again we are going to talk about intensity. Okay. But in this one, the fringes that we are going to take, bright fringe, dark fringe, here also will come, right? But the intensity of all fringes is not same. In Young's double slit experiment, what we saw, maximum intensity of all fringes same. Minimum intensity 0, maximum intensity same, but here it is not. Here we are not going to get the same intensity for all maximas. Minimum intensity will be 0, no doubt, but intensity of all maximas will not be same. Second thing, fringe width also will not be same for all maximum intensities. Fringe width will also not be same. Remember that. So that is the difference between diffraction and interference, Young's double slit experiment. Okay. So what I told you here, intensities of all maximas. Intensities of all maxima is not same. Same way, fringe width is also not same. Central maxima has largest fringe width. Central maxima has largest or biggest fringe width. Okay, so this is mainly the difference. Now, second difference is, as we said that in interference there were two sources. So that was basically the interference of two waves coming from two different sources. But here there is a single slit only. It's a single slit. So in a single slit then, these two waves we are taking from what? From secondary sources. Secondary sources of the same slit. They are producing the waves, they are interfering. So because of that reason, the fringes are also not same here and the intensities are also not same. Okay. Now let's talk about the central maxima. Now suppose central maxima is forming here. At this point shall we take? No. Yeah. Because we know that at central maxima, path difference needs to be 0. Like this. This is central maxima. Okay. Now maxima is surrounded by what? Minima. So here will be minima. First minima and here will be first minima. And what is fringe width? Separation between two successive minima or successive maxima. Okay. So this is the fringe width of central maximum. Short like this. Okay, like this. So now it is surrounded by two minimas, which are first minima here and first minima here. Now what we are going to do? We have to find their positions. We have to find fringe width also. We have to find their position also. Okay, how much is the position? Because those are the questions which will be asked from us. So position of first minima. The position of first minima, when we are going to find, there is a criteria which is given to us by Fraunhofer. What is the criteria he gave? That we will see now, and we will calculate its position. Okay. So here it is. Let's make one slit. It's here, and a screen which is here. And what we are looking for? First minima first. Okay. So we are looking for first minima. Let's say first minima is here. Okay. This is the position of first minima. And minima means what? Minima means where intensity will be 0. Okay. First minima. Intensity 0. How much should be the phase difference? Phase difference should be pi. Delta x should be lambda by 2. Okay. So 2 points you have taken. This is A and this is maybe take B. And this is point. So what Fraunhofer said, if you want your minima, if you want 0 intensity, then between these two, if we say that this is one source and this is one source, secondary sources, but do we feel that these two sources only will be there? There will be multiple sources here in between also, because from here directly all the light is coming. The plane wavefront is here. This is all the part of a single wavefront. So there will be multiple points like this in between. So all will be responsible for your minima or maxima or whatever we are saying. So Fraunhofer says that you better is divide this into two zones. Okay, divide this into two zones. Okay, so here we divide it into two zones. One zone, two zone. First zone, second zone. Now, all the sources which are there in here and all the sources are there here. Okay, they'll produce delta x equal to lambda by 2. Then only it will have minima. So, okay, fine. So, what we will do? Here and here. Now, suppose this distance we are going to take a small d. Okay, this is small d. And this we have already taken as capital D. Okay, so this is d by 2. And this is d by 2. Okay, now I'm going to talk about this alone. I'm not going to talk about remaining. I'm going to talk about this alone. So here for me, this is d by 2. Okay. And from here this one and from here this one. Right? Now what is the path difference between these two? We'll say for path difference, we are going to drop a perpendicular over here. This will be path difference, delta x. And then this I am going to consider as theta. Exactly same thing what we did in interference. So delta x here is what? D by 2 sine theta. There we used to get d sine theta, here d by 2 sine theta, because we divided into two zones. Okay, so d by 2 sine theta. But what is delta x? Say lambda by 2. Okay, so that means sine theta equal to lambda by d. We got sine theta value. Okay, now then what? The position I wanted y value. So join this one. Central maxima's position is here. Okay, and this value we call as y. Here we got theta. Okay, so what is theta? This is theta basically. And if you want to drop a perpendicular here, drop a perpendicular here. This is perpendicular, this is perpendicular. Okay. Alright. Then sine theta equal to lambda by d. That is also fine. Okay. Now this theta you see in this triangle. Now this triangle says tan theta equal to y by d. theta, theta, small angles, very small angles. So since theta is very small, you can write it as y equal to lambda d by d. So first minima is at what position? Lambda d by d. The same way here also first minima is there, that is also lambda d by d. So what is the fringe width of central maxima? Because central maxima is there in between them. We have made it like this. See, first minima, and this is central maxima. So what is the fringe width of central maxima? 2 lambda d by d. So beta for central maxima is what? Lambda capital D by d into 2 lambda capital D by d. Okay, this is here. Then if suppose that we want to search first maxima, then what we have to do? So according to Fraunhofer, in that case we are going to divide this zone into three parts. Okay, for first maxima, we will divide the zone in three parts. Okay, so for maxima, remember always the zones will be 2n plus 1. And for minima, zones will be 2n. Zones. In this one, even number, here it is odd numbers. So the first maxima means 2 into 1 plus 1, that means 3 zones. So in this one, what you will say? You will say delta x is d by 3 sine theta equal to what? Lambda by 2, not lambda. Because here criteria is, suppose we are going to talk about 3 zones and all 3 zones are producing the waves, then 2 zones will cancel each other. Okay, in diffraction we always talk about cancelling. Okay, so if 2 zones are cancelling, one zone will still have light and that light only will be coming for first maxima. That's why the intensity decreases. Okay, at central maxima, both the waves are reaching in same phase. Both are giving you interference, so you are getting maximum intensity. First maxima, in the same one, in the same here, you made 3 zones, and out of these 3 zones, 2 zones are cancelling each other. Only 1/3 is remaining. So 1/3 light only is coming over here. Second maxima, when we talk, we take 5 zones. In that 5 zones, 4 zones cancel each other, and only 1/5 of the zone gives you light. So obviously intensity is decreasing. This is how Fraunhofer has given us the direction. How can we find out the position of the first maxima, second maxima, third maxima? I'm just writing the formula, but first you see, first maxima is what? So here this first maxima sine theta equal to what? 3 lambda by 2. Okay, so that also will be 10 theta's value. 10 theta y by d. So y value here for first maxima comes out to be 3 lambda d by 2. So how will be writing the position of maximas? We'll write position of maxima. From here only we can see, okay. From here itself we can find out positions of maxima. Okay, so y will be 2n plus 1 lambda d by 2. You put n value, first maxima, second maxima, third maxima, you'll be getting. Okay, same way y for minima. What do you get? 2n lambda capital D by 2. First minima is there. First minima 2 into 1. Or 2 into 1 is actually beta, not y. Sorry. Here y we are writing. So y is n. N lambda d by 2. Okay. So n equal to 1. So 1 into lambda d by 2. First minima's position. And second minima's position, what you will do? In second minima's position, we divide the zone into 4 parts. So it will become d by 4 sine theta equal to lambda by 2. So sine theta will be equal to what? 2 lambda by d. So y will be 2 lambda d by 2. So same thing. That's what we have written, n lambda d by d. So if n equal to 2, 2 lambda d by d. So this way you can find the position of first minima, second minima, third minima, first maxima, second maxima, third maxima. What is the fringe width also we can find, right or not? Fringe width also we can find. So central maxima's fringe width you already found, correct? Same way we can find out the fringe width of first, what to say, first maxima. This is 0th maxima. If I say first maxima's position also we can find. What will be first maxima? Separation between first minima and second minima. So first minima is what? This. Second minima 2 lambda d by d. So what will be the separation between them? Lambda d by d. But central maxima is 2 lambda d. So see, fringe width decrease. As you keep going up, it will even more decrease. Okay. So not only fringe width is decreasing, even intensity also decreases in diffraction pattern. It's not like interference. Okay. So questions will be what? Positions. Okay. Position between this, difference between third maxima and second maxima, fifth maxima, like that they can ask you. Okay. So this is what mainly they will ask you in diffraction. Okay. Angular width also they can ask you what is the angular width of central maximum. What is angular width? How we used to say beta by d, beta by capital D. So it will come 2 lambda by d. Okay. Angular width means beta by capital D. Remember that. Okay. Right. So this is what we have in diffraction. Then is polarization. What is polarization? What is the meaning of polarization? Now, polarization is the phenomena through which only we could say that light is basically a transverse wave. Okay, this was the proof of transverse wave. So, in polarization, what we do? We are limiting the vibration of the particles along one plane. Here, if suppose that there is a source. Now, we all know that because of this source, the light is going or the energy is going in all the directions. X, Y, Z, all the planes. How many planes we have? 3 planes we have. In all the planes it is going. But if we are restricting it to vibrate only along one plane, then we are doing polarization. Okay? Restricting vibration of particles along one plane is called polarization. It's called polarization. Okay, so when we talk about unpolarized light we show in this way. Okay, we'll be showing that this is vibrating like this. Maybe this we can say along y-axis. Okay, then we can say that okay, this is vibrating along x-axis, and then they are vibrating along z-axis also. That also we can show like this. Okay, this way we can show. But now what we are doing is we are making it to vibrate only in one direction. In one direction actually it's moving. Okay, suppose along x-axis it's moving. The light's direction is like this. This is how the wave is moving. And we are restricting it to vibrate only in one direction. So what do you say? They will be vibrating like this, or we will say it's vibrating in this way. Either this or this. Then we will say yes, we are polarized. Polarization has happened. Now that is also there. Now if suppose that unpolarized light is there. Okay, this is unpolarized light. So when you are going to polarize light, obviously intensity also is going to decrease. From here intensity, here it will be decreased. So polarization is also a process in which you decrease the intensity of light. Certain polarized glasses are coming, which the people will be wearing. So what happens when the light enters into their eyes? The intensity of light gets decreased. Okay, so they can see properly even when they are in sunlight. Normally what we happens when the sunlight comes, we tend to block it, okay, because we cannot see properly. But when you are using polarized glasses, you are able to decrease the intensity or glare that is coming in your eyes. Okay. So polarization basically is making the particles to vibrate along one plane. Right? So what we have two processes through which we do it. One is Maloo's law and another one is Brewster's law. These two only we have in our syllabus. So let's talk about Maloo's law first. So Maloo's law says there are certain devices which call as polarizers. Polarizers have got a particular shape. Okay. So particular shape is there. This shape. We make polarizers like this. This polarizer. So when light passes through this polarizer. Okay. So if suppose I say, but I have to rotate this first. If I can, let's see. Not in this way. Not this way, I have to make it. Okay, fine. So this basically is a polarizer. But if suppose that we want to show it that this is the light here, okay, which is unpolarized. Unpolarized light is coming, in which particles are vibrating like this also, and like this also. Along y-axis also, along z-axis also, this way also we can show, which will be one more side, but that's okay. We are showing it like this. This is unpolarized. Now this polarizer we are keeping. Okay, so polarizer I am keeping like this way. It's tough to make. Hexagonal, I am not making hexagonal, I am making it as rectangular. Like this is our polarizer. Okay, now its plane is what? Like this it is. Okay, so it's going to allow only those vibrations which are parallel to its plane. Okay, what is its plane actually? This is the plane. Okay, so it will allow those vibrations only which are like this along y-axis. Okay, so we can show it through this one. We can make little opening over here just to show that okay, what vibrations is going to clear. So it's going to clear only vibrations which are along y-axis. This z-axis vibration it will absorb. So when it's coming over here, it will be like this. These are the vibrations which are coming up. So if unpolarized light is here, if its intensity is I naught, then here our intensity becomes I naught by 2. Okay, so intensity became half immediately. Now, suppose we are having more polarizers after this. So, after polarization, if you are using one more polarizer, we call them as analyzers. Okay, after polarization process, if you are having more, then we call them as analyzers. Why? Because you have already did the polarization. Now it's having vibration along one plane only. Now, further, if you are using them, that means you are trying to decrease the intensity only. That is only the purpose. Okay, you will be able to increase the intensity only. You are not decreasing its vibrations. You are already done. Okay, it's already along one direction. Now you can't decrease it further. You can decrease its intensity. So if suppose you are using analyzer, more analyzers you are using over here. Okay, so let's make it over here one more time. So analyzer we are using in this way. Okay, like this it is. So it is tilted. From this, you have tilted it like this. How much we have tilted it? Let's say theta. Okay, from vertical, we have tilted it by theta. Okay, so what will be the intensity which will be coming out, and how will be that? Here I am showing the vibrations like this. Now, how will be the vibrations over here? Now, vibrations will only remain along the plane. So, vibrations will be like this now. like this will be the vibrations. Okay, like this will be the vibrations. And what will be the intensity? Intensity is also given by Malus. Malus says that whatever is intensity over here, let's say this is I1. So here intensity will become I1 cos square. Here intensity will become I1 cos square. Right? And suppose one more we make. For your clarity, I am going to make one more analyzer here. Okay. So one more analyzer. It's like this time. Okay, like this it is. So now from the previous one, from this one, so this is how it's maybe like this. Okay, maybe it's like this. And from this, suppose it's making an angle phi. This is phi. What will happen now? If I say that this is I2, then this will be I2 cos square phi. Here intensity will become I2 cos square phi. Okay, be like this. Clear? Now phi is what? Phi is the angle made by this analyzer with this analyzer. So this way intensity keeps on decreasing. Okay, this is Malus. First you polarize it already with the help of polarizer, then you can decrease the intensity further. So question can be asked from you in this way. First polarizer is 45 degree, second polarizer is making 30 degrees or maybe 60 degrees, whatever. Like that they can ask you and they can ask you what is the intensity. Okay, direct questions will be there, nothing is there that they can make the question complicated in that. Okay, so that's Malus law. Then what we have? We have Brewster's law. Brewster's law is what? And Brewster's law, it says that if unpolarized light is entering into medium, okay, it's entering into a medium in such a way that there is reflected light as well as refracted light. There is reflection also. Okay, there is reflection as well as refraction. And refraction and reflection is such that both are perpendicular to each other. Both are perpendicular to each other. Okay. Both are perpendicular. This angle is 90. This is unpolarized light. In this one, both components are there. Okay. This is also there. And this is also there. This is unpolarized. So if unpolarized light is coming and there is reflected light and reflected light and refracted light, both are perpendicular to each other, then this reflected one is polarized light. Okay, this will be polarized. So you can make it like this. This alone. Okay, so this is polarized. Plain polarized. Here, we partially polarized. What is partially polarized? It means is intensity decrease. Okay, intensity in this direction is decrease over here. Okay, but it will have both. It will still have both. Like this. Okay. So now what? You want to know what is this angle of incidence at which this is happening. Okay. What is this angle of incidence? Now we know that this is angle of incidence, then reflection angle also will be I only. No doubt about that. And this is angle of refraction. So we can see that here I plus R plus 90 equal to 180. I plus R plus 90 equal to 180. So I plus R equal to 90, R equal to 90 minus I. So if you apply Snell's law over here, it says 1 sin I equal to mu sin R. Now what is mu? Coefficient of refractive index of this medium. 1 sin I equal to mu sin R. Okay? Sin I equal to mu sin of 90 minus I. Sin of 90 minus I means what? Cos I. Sin I equal to mu cos I. So that means tan I equal to mu. I equal to tan inverse. Now in this question, or this formula rather, many times I have seen this. Many times. They may not say Brewster's law, but they will say reflected light and refracted light are perpendicular to each other. Mu will be given, they will be asking you angle of incidence, or I will be given, they will be asking you mu. Many times I have seen. So this is what Brewster's law is. And in this one, which light is plane polarized? Reflected light. Okay, refracted is partially polarized. So these are the two things that we have in polarization. Okay, that's it as far as wave optics is concerned. Now we are moving into electromagnetic waves. Okay, in electromagnetic waves, first thing that we are going to do is displacement current. Now what this displacement current is? Displacement current we can understand by capacitance. Okay, so suppose that I am taking circular plates of a capacitor, it's like this. Okay, and we connect this capacitor with the battery. Okay, let's connect it. Alright, then finally then connect it, and here we'll keep a battery. There is a battery like this. So when we connect it with a battery, we know that what happens in a capacitor. From here electrons will go to positive plate of the battery, and these electrons then move to this negative end of the battery, and then those electrons will be going on to this one. So this way here will come positive charge, here will be negative charge. So will it be charged immediately? No, it takes time. So that means the charge which is coming on this plate and the charge which is coming on this plate, okay, will keep varying for some time, keep increasing for some time, then only will know it's fully charged. Correct or not? So it will keep on varying. The charge keeps on varying. That means there is a current in this. When capacitor is fully charged, then what is the current? There is no current after that. Here also potential difference V, here also potential difference V. In that case, there will be no current flowing when it is fully charged. Okay. When capacitor is fully charged, then there is no current in the circuit. There is no current in the circuit. So then, till what time current is there? Till you are getting charged, or till you are charging this capacitor. So when charging the capacitor means charge is changing. Okay. If charge is changing, then electric field between the plates also will change. There is electric field from positive charge to negative charge. Like this electric field is there. Right? There is electric. What electric field? Sigma by epsilon. It's a capacitor. The electric field is sigma by epsilon naught. Sigma is what? Q by A. Q by epsilon naught A. This is electric field. But is Q constant? Say no. It's varying. Q is varying. Okay, Q is varying. Fine. So I want what? I want current. It's a displacement current. So current will go dq by dt. So differentiate that. Say dE by dt equal to dq by dt by epsilon naught A. dq by dt is current. So bring this one here. Say epsilon naught A dE by dt equal to dq by dt. Okay, but this electric field is between what? Between the two plates. So that means this current is there between the two plates. And current always is from positive charge to negative charge only. So current is like this, ID. Call this as displacement current. And what is this? Just see this here. dq by dt. Now I am writing this as epsilon naught A into d. I am saying is this is actually d phi by d. E into A is what? Electric field into area vector. That is flux, electric flux. So epsilon naught change in flux is equal to displacement. This is displacement. Epsilon naught d phi E by d. Now is it because of electrons motion? No. Electrons motion is happening here. This is not for electrons motion. Electrons motion is there. Okay, and the current which is coming because of electron motion is called conduction current. IC is conduction current. Okay, and ID is displacement. Okay, otherwise how it was like if we suppose we want to apply Kirchhoff's law. Kirchhoff's law is applied only in closed loop, right? Loop's law. So Loop's law says that current moves an entire loop. But when you have capacitor, the capacitor is not connected. So how the current will flow from one plate to another? For that only this idea came, the displacement current. Between these two plates, because there is no connection between them. So there is no possibility of conduction current. So then what current is there? Displacement current, which is because of change in electric field. In EMI you saw that if you change the flux, magnetic flux current is there. Here you are seeing that if there is a change in electric flux, then also there is a current and we call this as ID. Okay, and remember, between these two plates, conduction current is not there. Outside the plates, displacement current is not there. It means always conduction current's value will be equal to displacement current value. Always this is equal. Remember, sometimes intentionally the question asks you what is conduction current and they will give you all this value so that you can calculate displacement current. Okay, but they ask conduction current. So what we have to do? Okay, fine. We calculate displacement current. We say that value is C. Okay. So this is displacement current. Now can we have another few more forms of this one? Yes, we can have more forms. What forms we can have? See, charge on capacitor I can still write as CV also. So if current we have to find, current we can write as dq by dt. Okay, so if C is constant, then what is changing? V is changing because entire potential will never come at once. Slowly potential will drop because charge is also slowly dropping. So I can also be written as C into dV by dt. That is also possible. Okay, and another one I already told you. This is like epsilon naught A dE by dt. If electric field is varying, then okay, fine. Electric field is varying, then we can calculate displacement current like this. Right. So these are the various forms, and then the question will be asked from us. Shall we solve the question? Okay, let's see. So question number 1 says potential is changing with time and capacitance is given to microfarad. ID we have to find at t equal to 1 second. So that's easy, right? That's easy. We know that Q equal to CV. So I means dq by dt. That means C into dV by dt. dV by dt will give us what? 2t plus 2. Okay, time is also given 1 second. So 2 into 1 plus 2, that is 4. C into 4. This is 2 into 10 to the power minus 6 into 4. So 8 into 10 to the power minus 6 ampere or 8 microampere. That will be displacement current value. What is conduction current? Same. Okay. Another question is there. Similar question. So V only is changing here also. But in this one, information given is different. Area of the plates of capacitor 2 and separation between the plates of capacitor is D, and you have to find ID at T equal to 2 seconds. So first we have to write the capacitance, and then we have to do it. But first let's do dV by dt. So dV by dt is 60. Okay, and T equal to 2 seconds means dV by dt is 12. Okay, now what? C we will find. C is what? Epsilon naught A by. We know that epsilon naught, if you want, you can keep the value 8.85 into 10 to the power minus 12. Area is 2 and D is 10 mm. 10 into 10 to the power minus 3. That means 10 to the power minus 2. Okay. So this will come out like this is 0. This is 7. And this is also 7. Okay, 17.70 into 10 to the power minus 10. So this is capacitor. So dq by dt or ID will be C into dV by dt. C is this and dV by dt is this. 17.70 into 10 to the power minus 10 into 12 ampere. Right? This way we can do. Then what? Okay. Next question is given in which E is varying electrically. So E between plates is given to you as 2t square plus 2. Area of plates is given 6 meters square, and you have to find displacement current. Okay. What to do? Now we already have said that ID basically is epsilon naught d phi E by d. Okay. Now A is given constant. So epsilon naught A you can take constant. Then what is here inside d by d? That is it. Yes. So let's put it everything. 8.85 into 10 to the power minus 12. Area which is 6. And d by dt means differentiation of this will be 4t. So 4t. Then I have to give you time also. At what time? Find ID at t equal to, anytime you can take 2 seconds only you take. So what we are getting? 8.85 into 10 to the power minus 12 into 6 into 8. This will be 8, right? So 48 ampere. That's all. So easy questions. Okay. Easy questions are asked on displacement current. Okay. One more question is there. This is capacitor here. This is capacitor. Its capacitance is 2 microfarad. Potential is varying. Question is asking what is the displacement current in between plates of area of radius 1 meter. That means he is asking here how much is displacement. Not in entire capacitor he is asking. He is asking on this. Okay, no problem. So displacement current we know already is actually here what V is changing. So we know that ID is basically what? C into dV by. Correct. Now the question is what is C of this one? dV by dt we can find any day. What is C of this 1 meter radius plate? Okay. So larger ones C is given. So what this 2 is, 2 microfarad actually is epsilon naught. Area is pi into 3 square by d. Now whatever is d for the bigger capacitor, same is d for the smaller one also. So I am not bothered about d as such. Okay. So here you see this is 2 microfarad by 9 pi. This 9 pi. That's the value of epsilon by d. Correct. Now I want to find capacitance of that smaller one. Let's say this is C1. Okay. So C1 will be what? Again it's epsilon naught A by d only. The epsilon by d value you already have. 2 microfarad by 9 pi. Now area now is what? Pi into 1 square. Because this area, this radius is 1. So pi into 1 square. Okay, so pi and pi gets cancelled. So now your capacitance has become 2 microfarad by 9. We'll keep it here. What else? Okay, 2 into 10 to the power minus 6 by 9 into. Okay, now differentiation of this. What is that? 80. Again time, not given. Okay. So what is displacement given between place of area of radius 1 meter at t equal to 1 second. Okay, so we'll keep it over here 8. So 2 into 10 to the power minus 6 by 9 into 8. That's all. So this will come 16 by 9 into 10 to the power minus 6. Okay, that's all. This is the displacement current you have. Okay, so any type of question asked, you can do it. Simple concept, but yes, questions are asked on displacement current. Okay. Okay, what are the laws of EMI here? We have seen all except this. Okay, so this one is what? Our Gauss law is there. Okay, surface integral is equal to charge inside by epsilon naught. Okay, EDL, line integral of electric field is equal to d phi b by dt. What is that? Induced electric field. Induced electric field. This we saw in EMI. Right. This is what this we have not seen. Okay, what is that? Surface integral of magnetic field, and that's equal to 0 because you don't have monopoles. Dipoles are there. If a dipole is there inside the Gaussian surface, then what will be the magnetic flux linked with that? 0. Okay, because north and south pole both are there. So magnetic flux linked is 0. This is Gauss law only in magnetism. Okay, Gauss law in magnetism. And what this is Ampere's law. Ampere's law we have seen line integral of magnetic field is equal to mu naught I. But here we have added this is IC plus ID. Because between the plates of capacitor also magnetic field is found. Okay, where? Let's see, I'll show. Here. Okay, in this one there is displacement current. So if I am going to make or I am going to bring, let's say compass you are bringing. A compass if you bring here all around it, you will be finding there is deviation in the magnetic compass because magnetic field will be produced because of conduction current. Same way here also. Here also if you are bringing magnetic compass there will be deflection in that. At the same time when you are bringing the magnetic compass here also there will be deviation. That shows that yes there is a current but that is not conduction current, a different type of current. Okay, so here it will be only ID, here will be only IC. So Ampere's law there was a correction made that it is because of both conduction current also and displacement current also. Okay, so V dot dl equal to mu naught IC plus I. Right? Okay, now we are moving towards electromagnetic waves. So what we were doing, subtopic was displacement current in electromagnetic wave, we saw that. Okay, so now EMW. So electromagnetic waves, we know that light is electromagnetic wave. Non-mechanical wave doesn't require any medium for propagation. Okay, who is producing it? Now, light in general is produced only by or coming from the sun at the moment or from stars. Okay, but there are different forms of electromagnetic wave that can be produced by in a different forms. So one form is accelerating electrons. Now accelerating electrons also produce electromagnetic wave. Which one? X-rays. X-rays is produced by this. Okay, de-excitation of atom. De-excitation of atom also electromagnetic waves are produced. Okay, electromagnetic waves are produced. Sometimes there will be ultraviolet rays are produced, visible rays are also produced, infrared rays are produced. So these are also part of electromagnetic waves. So de-excitation of atom also we get electromagnetic waves. De-excitation of nucleus. Okay, in this one what we got? Infrared, ultraviolet, visible and infrared. Okay, de-excitation of nucleus gives you gamma rays. Okay, so these are the types of things that is normally produced. We can produce them. Okay, alright. Then not produced by electromagnetic waves are not produced by charge at rest. You know the charge at rest only produce electric field. So charge at rest do not give any kind of electromagnetic wave. Orbiting electron around nucleus is not going to do anything because orbiting electron has a constant energy. Okay, but when it jumps from one orbit to another orbit, from higher energy orbit to lower energy orbit, that means I have written de-excitation of atom. And that one definitely it is going to release a photon which belongs to electromagnetic waves. Okay, so this is how electromagnetic waves are produced. Okay, now what more we know about electromagnetic wave? As I told you that these are medium independent. Medium independent. That means they can travel in all medium. Speed of light, c equal to 3 into 10 to the power 8 meters per second in vacuum. Okay, but in terms of a formula, we write it as 1 by root over epsilon naught mu naught. In free space, this is permittivity of free space, this is permeability of free space. So c equal to 1 by root over epsilon naught mu naught. In any other medium, let's say we say V, it will become root over 1 by epsilon mu, permittivity of medium, permeability of medium. But we all know this permittivity of medium, epsilon, we can write as what? Epsilon r, epsilon naught. Okay. Epsilon can be written as epsilon r into epsilon naught. Same way mu can be written as mu r, mu naught. Okay, relative permittivity and relative permeability. So if we are going to write in this one, then 1 by epsilon r, epsilon naught, mu r, mu naught. Now we have written already 1 by root over epsilon naught mu naught is c. So here also 1 by root epsilon naught mu naught is c. So that means this v is actually equal to c by root over epsilon r mu r. V is equal to c by epsilon r root over epsilon r mu r. But in light we saw, what we saw? Coefficient of refractive index. V is equal to c by mu. Mu, there was coefficient of refractive index, and mu is what? C. This is mu. Root over epsilon r mu r. That is coefficient of refractive index. Okay, this way we can correlate that. So this is the speed of light in medium. This is in vacuum or air. Then, as the medium changes, we all know that we have studied in waves, frequency doesn't change. So frequency, yes, do not change. Speed changes and wavelength changes. Clear? Okay. More what we know about this light. More we know that the speed of light c is actually the ratio of E naught by B naught. What is E naught? Magnitude of electric field by magnitude of magnetic field. When we talk about electromagnetic waves, We are saying that it's medium independent. Then what about the vibration? It's a wave, so vibration of particles. So in this one, vibration of particles are not there. Okay, there is no vibration of particles. Then what is vibrating? Electric and magnetic. Okay, electric and magnetic field are vibrating. Electric and magnetic field are vibrating. Are changing periodically, sinusoidally. That means we can represent them with the sine function or cos function. Are varying sinusoidally. Okay, so electric field I have to write, then electric field I will be writing in this way, E equal to E naught sine of say kx minus omega, and magnetic field I will be showing as V naught sine kx minus omega. So that means electric field is also moving along x-axis and magnetic field is also moving along x-axis. Answer is yes. Both are heading in the same direction. But is the vibration also along same direction? Answer is no. Vibrations will be perpendicular to each other. This is the direction of motion. Okay, but vibrations will be perpendicular. So if suppose I say this is electric field, this is moving along positive x-axis, but it's vibrating along, let's say, y-axis. Then the vibration of magnetic field will not be along y-axis. In fact, it will be along z-axis. It will be along z-axis. Okay, remember that. So both of these will be perpendicular to each other, and the velocity will be perpendicular to both of them. Speed of light or velocity of light will be perpendicular to both of them. And the relation is C equal to E naught by B naught. So if suppose I know E naught value, then I can write magnetic wave also. If I know B naught, I can write electric wave also. Many times this question is asked. They will give you electric field, they will ask you this. If they will give magnetic field, they will ask you this. Okay. So be careful, use this formula so that you can find this simple thing. Okay, what this is now? Now this is actually the information which is given in NCERT and we should know about electromagnetic waves. What electromagnetic waves we have? We know that if I write, okay, what electromagnetic waves we know about. So we will say that, okay, we can say on this side if we will use radio waves. Okay, then microwaves. Okay, radio waves we are using, microwaves we are using, infrared you will use. Then visible region you will be using. Then ultraviolet is there. Then X-rays is there. Then gamma rays. This is our spectrum. Okay, radio, micro, infra, visible, ultraviolet, X and gamma. When we move from radio waves to gamma, then wavelength actually is decreasing. Wavelength is decreasing and frequency is increasing. And what about speed? Speed is same. Electromagnetic wave, the speed of light. Speed is same. Okay. So all parts of this spectrum, they move with same speed of light, but as you move from radio wave to gamma, wavelength is decreasing, frequency is increasing. That means energy is increasing. When you are moving from radio wave to gamma, energy is increasing. Gamma wave has a lot more energy as compared to radio wave. Okay, so that is one part. The second part is they can ask you the questions based on certain informations which is given in our book. So we need to know that. Okay, so what are important things in that? Let's see if we can highlight that one. Where is our highlighter? Okay, so let's see. This is laser pointer, this is not highlighter. Is this the highlighter? No, is this one? Pattern pen, this will be highlighter. Yes. Okay, so what are they to highlight? Radio waves are produced by this one. Okay, accelerated motion of charges. Radio waves are produced by accelerated motion of charges. As we said, electromagnetic waves are produced by accelerating charge. So here it is. Radio waves we are producing with accelerated motion of charge in conducting wires. Okay, now where are they used? In radio communication, television communication, mobile communication. Okay, so all types of communication we use radio waves. See, they are used in radio and television communication system. They are generally in the frequency range 500 kilohertz to about 1000 megahertz. Okay, where we are using, that's important. This frequency we can leave also. Okay, right. So where it is now? AM. This is radio wave. We use in AM. Now AM and FM radio communication are those. Okay, AM and FM. So in AM he is writing amplitude modulated band. Then you have short wave bands. Then TV waves are there. Okay, this is TV waves. And then finally he has written FM. And you can see that as you are moving from this AM to FM, frequency keeps on increasing. AM is in kilohertz 530 to 1710. Then it goes up to 54 megahertz when you are using short wave bands. Then TV waves 54 to 890, and then finally MF 88 to 108 megahertz. Okay, so frequency keeps on increasing, and finally there will be cellular phone. That means our mobile phones use radio waves to transmit voice communication in the ultra high frequency. So these are used for communication. Okay, so radio waves are used in which communication? Radio communication, television communication, and mobile communication. Okay, this is what we have, and the range you can see is from somewhere from 500 kilohertz to 1000 megahertz. This is the range. Okay, this is the radio. Then next one is micro. What we have microwaves then? What is given in our book? So microwaves are actually short wavelength radio waves. Very similar to radio waves only, but slightly less wavelength, more frequency. Who's producing them? With frequencies in the gigahertz range are produced by special vacuum tubes called klystrons, magnetrons, and gun diodes. Okay, these are producing klystrons, magnetrons, and gun diodes. Due to their short wavelengths, they are suitable for the radar system. Radar where is used? In fighting planes, in defense. Okay, to detect the enemy planes and other things, drones and other things, right? So due to their short wavelengths, they are suited for the radar system used in aircraft navigation. Okay, and this radar also provides the basis for the speed guns used to time fast balls, tennis serves, and automobiles. Okay, so these are also used for different purposes, like tennis balls is there, and automobiles also it is used for detection purpose. Okay, tennis balls means is to serve. Okay, then what else is there? Microwave ovens. Everybody knows about microwave ovens. Okay, what in that one? What is happening? Microwave frequency matches with the frequency of water molecules. So at resonance, they pass more energy to water molecules and they start vibrating with higher amplitude. Energy is produced, and whatever food you are keeping, that will be cooked in that. Okay, so that all is fine. This raises the temperature of any food containing water. These are microwaves. Okay, then what we have? We have infrared waves. Infrared waves where we use in all the remote controls. Remote controls we use infrared wave. Okay, and it is produced by what? Hot bodies and molecules. Okay, hot bodies and molecules. And infrared is what helps keep the temperature of our atmosphere constant, or whatever the temperature is there, it keeps it. This is because of infrared waves. Okay, and there is more information is there, but this is what more important is there. In all remote controls we are using it, whether it's related to TV or whatever. Okay, and it keeps our surroundings temperature constant. This is only involved in what to say, greenhouse gases also. Okay, because that also absorb the heat from infrared waves. Okay. Then what? Ultraviolet rays. Ultraviolet rays, these are dangerous for us. Okay, very high energy they have. Wavelength is from 4 into 10 to the power minus 7, 400 nanometer, down to 6 into 10 to the power minus 10. That is 6 angstrom. Okay, this is produced by special lamps and very hot bodies. Now, sun is very hot body, obviously. Okay, produced by lamps and very hot bodies. The sun is an important source of ultraviolet light. Okay, and it's dangerous for us. Exposure to UV radiation induces production of more melanin, causing tanning and sunburn also. Okay, in welding also these rays are produced. That's why welders will be protecting their face with the shield. Okay, which absorbs the radiation. The glass normally absorbs all UV radiations. So that's why that screen they keep, or special glasses they keep, goggles they keep, so that this UV is not affecting them. Okay. Then what else? Where we use them? UV is also used to in filters to filter the water. Okay, it will be written how it is. Welders wear. Okay. UV radiations can be focused into very narrow beams for high precision applications such as LASIK. That is for eye views. Laser assisted in C2 keratomyolysis, eye surgery. Okay. And UV lamps are used to kill the germs in water purifiers. Okay, so it's used in LASIK also, that is an eye surgery, and it is also used to purify the water. For us, ozone layer protect us from UV rays. Most of the UV rays is absorbed by ozone, but ozone is having danger from, it is also written, chlorofluorocarbons, which comes out from refrigerator and ACs. Okay. Alright, let's go ahead. X-rays. X-rays is produced by accelerating electron. When you are going to bombard accelerating electron on any metal, heavy metal, then we get X-rays. Okay, so X-rays we are familiar with, because if suppose that any fracture happens in our body, we go for X-ray photograph. Okay, so those are X-rays only. It is dangerous for us actually. Okay, we should not be exposing too much to X-rays, because it can pass through our flesh. It can create harmful effects on us. Okay, it can destroy living tissues. Okay, and it is used for medical purposes. That's all, it's enough. Then you have last one is the gamma rays. Gamma rays are produced by nucleus. Okay, when there will be de-excitation of nucleus, this gamma rays are produced, and it has maximum energy. Okay, it has maximum energy. So if X-rays was dangerous, this is more dangerous, right? They are used in medicine to destroy cancer cells. So these are the information that we should remember as far as all this electromagnetic spectrum. Okay. Now what? Now let's see what the numericals are asked on electromagnetic. Okay. See. So question is given for magnetic field. Right. What the question is? Question is, magnetic field is 2 into 10 to the power minus 6 sine of 200 pi x minus 3 into 10 to the power 10 pi t. Find lambda, find speed of wave, and find electric field wave also. Okay, so what we'll do is, this is moving along x-axis, and this I will make that It is vibrating along y-axis. Then only we can find, otherwise it will be difficult, right? Okay. Sorry. Lambda. So we know that this basically is what? Kx. So k value is 200 pi. And k is what? 2 pi by lambda. Right, pi cancelled. Lambda is equal to 2 by 200. That is 1 by 100 meters. This is lambda. Speed of wave. Speed of wave is what? Omega by k. We know that. From wave we have learned it. What is v? Sorry, what is omega? This is omega. 3 into 10 to the power 10 pi. So 3 into 10 to the power 10 into pi by k. K is what? 200 pi. Pi gets cancelled. This is 3 by 2 is 1.5. 1.5 into 10 to the power 8 meter per second. Now from here we can ask you what is the coefficient of refractive index. Coefficient of refractive index will come as 2. Okay, fine. Then this. Now we can see that where is actually the velocity. Velocity is along positive x-axis. Kx minus omega t. So velocity is along positive x-axis. Magnetic field is along vibrating along y-axis. Okay. Now what is the relation? Relation is C. Direction only I am saying, not magnitude. Electric into magnetic. This is how the direction. These are all unit vectors, okay? Alright. So C is basically along x-axis given to me. E I have to find, I don't know. But this is J. So how can this be? I have K only we can keep because these two are perpendicular to each other. So if I am keeping K over here, the K cross J is minus I actually. So what should be E? Minus K. Now it's perfect. K cross J is minus I, minus or minus plus. Perfect. So our electric field is in which direction? Minus K. Now let's write electric field. Okay. So E equals E naught. Now V naught is given to you. What we know? C equal to E naught by V naught. C equal to E naught by V naught. So E naught is what? CB naught. Then same function. 200 pi x minus 3 into 10 to the power 10 pi t. And then what? Minus k. That's it. So 2 into 10 to the power minus 6 into 3 into 10 to the power 8. Okay. 200 pi t minus 3 into 10 to the power 10 pi t minus k. What we have here? 6 into 10 to the power 2. 200 pi t minus 3 into 10 to the power 10 pi t minus k. This is electric field. Okay. Then one more similar question. In this one, electric field is given and he is asking you magnetic field. But before that, lambda. So 6 cos 4y plus 6 into 10 to the power 10t. Direction is not given in this one. Okay. So without direction, we will write. Okay. So lambda is asked. So lambda is, this is k value. This is going in which direction? Going in a negative y direction. This is going along negative y direction. This given as ky plus omega t. This is going in negative y direction. The direction of propagation I am writing directly. Negative y. Okay. Alright, lambda. So lambda is first, k value is what? K value is 4. Omega value 6 into 10 to the power 8. Okay, but what is he asking? He is asking lambda only. No, why? K is 2 pi by lambda. Lambda equal to 2 pi by k. And k value is 4. 2 pi by 4. So pi by 2 meter. Lambda wavelength in meter only, right? Then direction we have written B equivalent is asking. Okay, no issues with that. So B equivalent is what? B equivalent is, we know that C equal to E naught by B naught. So B naught equal to what? E naught by C. E naught is given as 6. So 6 by 3 into 10 to the power 8. Okay, then remaining C. 4y plus 6 into 10 to the power 8. That's all over. Unit will change. Obviously, this will be Tesla, and this has to be Newton per coulomb or volt per meter. Okay, right? Then intensity of electromagnetic wave. Okay, now energy in electromagnetic wave is in both forms, electrical energy form also and magnetic energy form also. But on an average, if we talk about the density, energy per unit volume, it comes out to be either half epsilon naught E naught square or D square by 2 mu naught. We'll write over here. Okay, do we have the place? We'll create, or we'll here only we'll write. Okay, it's talking about energy. Energy in electromagnetic wave or energy density. Okay, so what we have is, in this one, electric form is also there, magnetic form is also there. So on an average, how much it is? Energy density. So energy density for electric one is actually 1 by 4 epsilon naught E naught square for electric form. Same way magnetic form, 1 by 4 B naught square by mu naught. On an average, I am saying, because they are varying. Because electric field is varying, E equal to E naught sin omega t. Magnetic field is varying, B equal to B naught sin omega t. Okay, so on an average, in one cycle you can see, this much is the electrical energy form per unit volume, this is the magnetic energy per unit volume. But total energy is what? The total energy is addition of both, which you can take in any form, be half epsilon naught E naught square or half B naught square by 2 mu naught. And surprising thing is, electrical energy and magnetic energy both are equal in magnitude. This and this are exactly equal. Okay, so if suppose we say UE is actually equal to UN. That's why when you add 1 by 4 by 1 by 4 and 1 by 4, then only half will come. So this is energy. Okay, this is energy. Now, when we are talking about intensity, intensity is what? Energy density into C. How? Intensity is what? What is intensity? Intensity is energy per unit area per unit time. Intensity, again I am writing intensity. Energy per unit area per unit time or power per unit time. Okay, but here it is given in terms of energy density. So what I will do? Energy multiply with x, area multiply with x. Now this becomes volume. So energy by volume. Energy by volume is energy density. X by t, distance by time, speed. So intensity comes out to be energy density into speed. Energy density into speed. Okay, half epsilon naught E naught square into C you write, or D square by 2 mu naught into C you write. So this is intensity formula, intensity of electromagnetic wave. Okay, momentum. What is the momentum? Now we all know that E is equal to mc square is the energy. Okay, in this one we can write as what? Mc into C. Now mc is momentum. Mc is momentum. So momentum comes out to be E by C. Remember, E is energy over here. Don't say electric field. E is energy. Or shall I write UV? Okay. So E is energy I have written. P is equal to E by C. Okay. Alright. Now radiation pressure. Radiation pressure. Pressure is what? Force by area. F by A. And force is what? Change in momentum per unit time. Okay. Change in momentum per unit time. Okay. Now there are two types of surfaces normally we'll have. One is purely absorbing surface, and other one will be purely reflective surface. Say purely reflective surface we have. Okay. Purely reflective surface. Reflective. So what will happen? In this one, energy will come and then it will be reflected. So if it is coming with momentum, which is E by C, it return back with the same momentum E by C. So what is change in momentum? 2p. Delta P is equal to what? 2p. Correct. Change in momentum is this. And we want change in momentum only in this case. Correct or not? We want change in momentum only. So change in momentum is happening 2p when we are talking about reflection. Okay, and momentum we are writing in terms of intensity, rather energy. Right. So what he'll be saying over here? Sorry. Okay. So what he'll be saying here? Delta P is what? 2E by C. Where E is obviously energy. Okay, we keep it in this one. So what we are getting is 1 by A, 2E by C, and delta T is still there. So T. Okay. So energy per unit area per unit time. That means intensity. Energy per unit area per unit time. Right? So 2I by C. This is pressure. Pressure exerted on purely reflective surface. If force you are asking, then 2I A by C. Force 2I A by C. Pressure is 2I by C. Force is 2I A by C. Now if pure absorbent surface is there, so if absorbing surface is there, what will happen? Let's see. It's absorbing. Okay, this is absorbing surface. So here, this is momentum of the wave coming, but it is absorbed. So return, there is nothing in this one. So in return, there is nothing. So that means change in momentum is what? P only. Okay, in this case, delta P is P. That means E by C. Delta P is E by C. Then force is delta P by delta T. So E by CT. Okay, here was 2E by CT. Here it is E by CT alone. Correct. Pressure, force by area. E by A into T. Energy per unit area per unit time is I. Pressure is I by C. Here it was 2I by C. Here is I by C. And force IA by C. Here it is 2IA by C. So remember that this kind of questions are also asked. Same thing we'll see in photons also. Now once this waves is over, we are entering into the modern physics. So in modern physics we'll see again. But same thing in terms of photon. Okay. Momentum of photon is also E by C only. Okay. Alright. Now let's see this question. Question based on this intensity and other things. What question is asked? This is a bulb here. 100-watt bulb is there. And this is the point P, which is at 3-meter distance. He is asking what is electric field strength at point P. Electric field strength at point P. What we can do is we can first talk about intensity. We can find intensity. Then we'll think about what is the relation between intensity and electric field strength is there. That we'll see later. First, let's find intensity. So, what is intensity? Intensity is power by area. Power by area. What is power? 100 watt. Area means 4 pi r square. Power by surface area, because this energy will be an entire sphere here. So, intensity is this. Then electric field strength. Now, intensity I can write as half epsilon naught E naught square into C. This only, no? Intensity we saw. Let's check. This was the formula. Where it is? Where we are seeing here. Yes. Intensity half epsilon naught E naught square C. Or if he asks magnetic, then this. Okay. Right. So half epsilon naught E naught square into C. So we can find it very easily. What is there in it? So 100. Here is what? 9 4 36 pi. Okay, epsilon naught we know, half is there, C 3 into 10 to the power 8 is there, epsilon naught we can find, no problem. Okay, then he is asking magnetic field also, no problem, here we will write magnetic field form, 1 by 2 V naught square by mu naught into C, that's equal to same thing, 100 by 36. No issues, mu naught value also we know, 4 pi into 10 to the power minus 7. C value we know, V naught we can find. Then he says find ERMS and BRMS. That is also no problem. Why ERMS and BRMS? Because electric field is varying sinusoidally like this. Magnetic field is also varying sinusoidally. We have already seen in AC how to find IRMS, right? Same way here. So if suppose he is asking ERMS, no issues. ERMS will be E naught by root. And BRMS is B naught by root. Very simple. How we got E naught? We got E naught from here, B naught from here. Simple. Okay. That's all I think. Yes. So this is it. Waves in general we have finished. Waves in sound, waves in light, electromagnetic waves, AC. 4 chapters are there in which wave concepts are used. Okay. So all we have finished. Tomorrow's class, let me see whether I can take semiconductors also or I can start modern physics. Let's see which way I am going. Okay. That's all for today. Scan, take the photograph of this. Takes a lot of time. Okay, finally it is here. So take the photograph.